Now, the reason that we use all of these scientific notations is because we want to make sure that we are the most precise and the most accurate as possible. So accuracy is a measure of how close a measurement comes to the actual value. So for example, this one has poor accuracy because it's not very close to our bullseye in the middle, which is our accepted value. This one also has poor accuracy because we aren't even close to the accepted number or the accepted location we want, which is the middle again. Whereas our last picture here shows great accuracy because they've hit the bullseye 3 times. Precision, on the other hand, is how close your measurements are to one another. So this one has poor accuracy because it's not close to that bullseye, and poor precision since all of these darts are far away from one another. This one has poor accuracy again because you're not close to that bullseye, but good precision because all of your marks are very close together. Finally, we have good accuracy once again because you're at that bullseye, but you also have good precision because they're all really close together. So when we are making our measurements, you want to try and be as accurate, so as close to our accepted value as possible, and precise. You want to make sure that all your measurements are rather close to one another. So with that in mind, there's always some sort of error that shows up. So suppose you use a thermometer to measure a pot of boiling water, and the thermometer only reads 99.1 degrees Celsius. However, water boils at 100 degrees Celsius, but you're making the observation that your thermometer is reading only 99.1. There is a way to determine how much error has occurred in your measurement. So we use something called the error value. So error is determined by the experimental value minus your accepted value. Your accepted value is the one that has been shown to be correct time and time again. Often it will be in the number in your book, whereas the experimental value is the one that you measure in lab. So if you think back to this question here, you have a thermometer reading 99.1, and you know that the real value is 100. Let's determine the error value. So we know that our correct value is 100 degrees Celsius, and that the one that we measured was 99.1 degrees Celsius. So according to our equation, we know that we need to take our experimental value and subtract it from our accepted value. So once again, 100 is our accepted value because you're going to find this one in a book, whereas our 99.1 is our experimental because that's the one you found in your lab. So to find the error, you take your experimental, whoops, I spelled that wrong, minus your accepted. So that would be 99.1 minus 100, giving you 0.9. That is your error value. So that's not a big difference because you're only off by negative 0.9 degrees Celsius, but that number really doesn't make much sense. You don't have anything to compare it to. So what we usually use is something called the percent error. That's how far away you are from the correct value. So our percent error is that error we just found, but the absolute value of it, so no matter what, it'll be positive, divided by our accepted value times 100, because that's how we make things into a percentage. So let's take our negative 0.9 value that we found from before and apply it to our percent error equation. So again, that's the absolute value of our error over the accepted value times 100. So our error is our negative 0.9 inside of our absolute value mark over our accepted value of 100. Then you are going to multiply your answer by 100 to get our percent error. And when you were to put that into your calculator, you would get our 0.9%. All of the work is also in your PowerPoint if you'd like to go over it at any point. So you are able to say that you are only 0.9% off of the correct value, which is pretty good. So we'll be using that at some point in our labs as we go along throughout the year.